Hi everyone, I'm Yanni. Today I'll be doing a lecture on energy levels in atom and line spectra. We learned from lower secondary that atoms have electron shells that are in layers. Now in grade 12 is a similar thing, but instead of shells is electron energy level. The electron in the lowest shell is called ground state, and the valence electron have the highest energy. Therefore, as an electron moves up its shell, its energy level also increases. There's a diagram here showing that the lowest energy level, also known as ground state, and so the upper ones are excited state. We'll learn more later that electrons don't stay long in the excited state. Lastly is the free state. Causing electrons to fully leave the atom, that process is called ionization. So now we need to know a basic concept, that is when energy is absorbed, electron moves to a higher level. And when energy is released, electron moves or transitions into a lower state. There are three spectrums that I'm going to talk about: the continuous spectrum, emission spectrum, and absorption spectrum. The continuous spectrum is a range of electromagnetic spectrum that consists of all wavelengths. It's usually seen when emitted by a light source such as the sun. Our sun emits white light, which is basically every color combined, giving the continuous spectrum. Next is the emission spectrum. The band shows the wavelength or color that an atom emits. Different atom emits different wavelengths. For example, iodine emits a purple color while bromine emits a brown color. Lastly is absorption spectrum. The dark bands are the wavelength that the atom absorbs, while the rest of the color is what passes through. Since energy levels in atom are discrete, the electrons only absorb and emit specific frequency, while the rest passes through. Now let's look at an example. When hydrogen absorbs light, only specific wavelengths are absorbed, as seen by the dent in the graph. And if we look up here, the electrons move up by specific levels depending on the frequency. Since purple light is higher frequency, the electrons move to a higher level as compared to red light. After absorbing, it isn't in a stable state. Therefore, the electron emits light back out and transitions to its original energy level. The color bands are the wavelengths that it emits. So if it absorbs purple light, then it also emits purple light. So how does all this apply in a real-life scenario? In the light bulb that we use daily, this is how the fluorescent bulb works. First, electrons are fired from the cathode. These electrons collide with the electrons of mercury vapor in the tube. The mercury electron is excited, then de-excited, emitting a UV photon. The photon then collides with the phosphor coating in the bulb. Now the phosphorus electron is excited, then de-excited, finally releasing visible light for us to see. Okay, now let's solve a problem together. It asks what wavelength is required for a hydrogen electron to be ionized. They gave us a diagram that contains the energy value for ground state and free state. And we remember that free state means ionization. So we need to use the formula delta E equals to Planck constant times time divided by wavelength. Now we just need to rearrange the equation. And this is what we got. H and C is constant and already given. We only have to find delta E, which is E final minus E initial. The final is the free state, which is 0 electron volts, and the initial or ground state is negative 13.6 electron volt. Minus it and we get 13.6 electron volt. Then we just have to convert it to joules by multiplying it by 1.6 times 10 to the power of negative 19. Now that we have all the variables, substitute them into the equation and our answer is 91.2 nanometers. So that is the wavelength required to ionize a hydrogen atom from ground state. That's it for this lecture. Thank you for listening.